Hi, this is a short presentation of our paper, entitled, Resolving Conflicts During Human-Robot Co-Manipulation. In our study, we focus on an object transportation task, where robot works side by side with human to manipulate an object from one position to another, safely, and without having a conflict with human partner. This collaboration emerges some interaction patterns between the human and the robot, and these interaction patterns have to be known by the robot to act accordingly. In this study, we trust that identifying and resolving conflicts is a key skill that a robot needs to be equipped with to execute co-manipulation tasks with a human. In this regard, we utilize features extracted from haptic data to build a random forest classifier that enables the robot to predict interaction behaviors. Also, we proposed a mechanism that allows the robot to proactively interact with a human partner based on the time series classification of the interaction behaviors. In our approach, the robot, initially, has no information about the target location, hence, it follows the movements of the human based on the magnitude and direction of the forces applied by human. Once the direction of human force vector settles, robot estimates an intended target location. An artificial potential field is generated to compute a trajectory for the robot to move the object toward the estimated target location. At this stage, the robot becomes proactive and moves the manipulated object collaboratively with the human partner. If the human changes the target during this manipulation, a conflict arises. We use a random forest machine learning model, trained with haptic-related features derived from the forces and torques applied on the object, to detect three interaction patterns. Working in harmony, where the partners agree on the target direction, hence, they move the object harmoniously. Conflict in target direction, where the partners face a conflict in movement direction as each aims at a different target location, and conflict in parking location, where the partners face a conflict in parking location since one of them aims to stop the motion of the object before or after the estimated target location. The random forest classifier detects these behaviors and notifies the interaction controller of the robot to generate a suitable response. For instance, if working in harmony pattern is detected, the controller maintains the proactive status of robot. On the other hand, if conflict in target direction is detected, the controller switches the robot role to a follower until a new target location is determined and a new trajectory is generated. Moreover, if conflict in parking location is detected, robot relinquishes its trajectory and acts as a follower to assist the human in parking the object. We designed and implemented two sets of PHRI experiments. First, the training experiments, which were designed to train and test the machine learning classifier. Second, the validation experiments, which were designed to investigate the potential benefits of the proposed approach in comparison to two other approaches. All experiments utilized the same setup shown in the figure. The objective in designing the training experiments was to collect haptic data to generate haptic-related features which were used to train a machine learning classifier that can effectively distinguish between different interaction patterns. To this end, 16 different manipulation scenarios listed in the table were introduced by covering as many different combinations of interaction behaviors as possible. In these training scenarios, human and robot collaborate to move the object from the starting location to one of the target locations shown in the figure. The training experiments were performed by 8 subjects. Each subject performed 32 trials, where each scenario repeated twice. After collecting the data, we split the dataset into 2 distinct sets, training and test. To train the classification model, we used the data coming from 24 trials of each subject and used the remaining 8 trials for testing. We achieved a classification accuracy of 88.82% and BER of 0.11 after cross-validation. The figure shows the confusion matrix for the classifier trained with the haptic feature set. To evaluate the performance of our proposed approach, we implemented another set of experiments utilizing the same setup shown in the figure. We considered 3 experimental conditions, C1, C2, and C3. The first condition, C1, implements a simple leader-follower model where the robot is passive and always follows the human. In C2, the robot has a fixed target location and follows a trajectory based on the artificial potential field method, regardless of the agreement or disagreement with human partner. Finally, C3 utilizes our approach of integrating the potential field method with the machine learning classifier for conflict resolution. 3 different experimental scenarios, ES1, ES2, and ES3, were considered for the validation experiments. In ES1, human and robot work in harmony to transport the object to a target position, B, while in ES2, the target location changes suddenly from location B to location E, causing a conflict in movement direction. Finally, in ES3, the target location suddenly changes from location B to location C, causing a conflict in parking location. 6 subjects participated in this experiment. Each experimental condition, C1, C2, and C3, was repeated twice for each experimental scenario. We used the average force applied by human and the average power consumed by human as metrics to evaluate the task performance of the subjects. The results of the experiments show that our approach, C3, reduces the average force applied by subjects by 42.65% and 30.6% compared to those under C1 and C2, respectively. Moreover, the average power spent by the subjects under C3 was reduced by 46.27% and 4.94% compared to those of C1 and C2, respectively. The following video shows a collaborative task under the 3 experimental conditions. In conclusion, we proposed an approach that allows the robot to proactively interact with a human partner based on the time series classification of the interaction behaviors that arise while executing a collaborative task. We showed that the features derived from haptic data alone are sufficient to detect the interaction behaviors emerged during PHRI. Our proposed conflict resolution mechanism reduced human force and effort significantly compared to the case of a passive robot that always follows the human partner and a proactive robot that cannot resolve conflicts. Thank you for listening.